Okay. So I'm going to start out answering a couple of questions with the vector review. For all of these questions, these vector questions, feel free to use your calculator. You don't have to do any of these by hand. I just want to make sure that you can do all these calculations. You're going to have to do these over and over again in the class. So really, like something like number 1 is just a matter of knowing how to enter this stuff into your calculator. Different calculators have different ways of doing it. So if you want help with that, let's talk about it after class. But yeah, let's go over a couple of the other ones. So
really quick, is T84, because I actually looked online, 89. That's like a really out of date, like outclass compute calculator. Like that's like a generation before these.
89?
Yeah.
No, 89 was after those.
I typed it in, it was telling me it was like it was the outdated version, but I could be confused.
I don't know. They still work well, but they their newest one that I'm aware of is called the Inspire, which has more than the 89 does, but the 89 is what I use the most. It has a good set of things. Okay, so for the vector review, so length of a vector, all this stuff is in the answers to how to do this stuff. It's all in the vector review, but the length of a vector is the square root of the sum of the squares of the components. So that would be, -5 squared plus 4 squared plus 8 squared. Take the square root of all that, and that would give you the length. So let's do a couple of the perpendicular ones. Okay, so what are 2 unit vectors perpendicular to 1, 2, 3, and 5, 2, 1? So this is number 4 in the vector problems. We want something, and not just something, we want unit vectors perpendicular to 1, 2, 3, and 5, what did I say? 2, 1. Okay, so how would you do this? The key operation here is that taking the cross product of 2 vectors gives you a vector that's perpendicular to the 2 inputs. So you can take a cross product, you can do 1, 2, 3 cross 5, 2, 1. Your calculator can do that for you. I guess if you have an 89 or an Inspire, it can. Otherwise, they're in the course information. I think it tells you how to enter programs that'll do that. I can help you enter programs that'll do that, but we'll do a lot of cross products, so it'd be helpful to have a program in your calculator that'll do this for you. To do it by hand, by the way, you'd go, so the x component, you'd cross out the first row and take this times this minus this times this. And that'll give you the x component. So 2 minus 6, so -5 is the x component. And then for the y component, you'd have a negative of, y is always the difficult one, so you'd have a negative of, cross out the 2 y components, and it's this times this minus this times this. So 1 minus 15, so that's -14. Yep. Wait, 2. I haven't learned my subtracts yet. Where's 2 by?
The x component for it. So you said it's -5. I was confused that too.
Oh, 2 minus 6 is -4. Thank you. Yes. Thank you for the math check on that. That was an approximation.
So is it because we have 1 times by 1? Is that why we get negative in front of the y?
The y always has a negative in front of it, and all this information is in that vector review. So if this stuff is hazy for you, I would spend more time reading through that vector review. Okay. And then the z component, cross out the 2 z components. 1 times 2 minus 2 times 5. So that's 2 minus 10. That's -8. Is that right, Cole? Okay. So -8 here. Okay, so when we take the cross product of those 2 vectors, we get -4, +14, -8. That is not a unit vector. So how do you get a unit vector? If you have a TI-89 or an Inspire, there's a function called unit v that'll do that for you. Otherwise, if you have a different TI calculator, you can very easily enter a program that'll do that for you, and then you never have to, basically we want to eliminate as much thinking as possible. So you're just sitting there punching stuff into your calculator. That's our goal. But to get a unit vector, so let's call this vector u, okay? Then the magnitude of u that you can write as an absolute value like this is -4 squared plus 14 squared plus -8 squared, all square root. Can someone calculate that for me?
Absolutely.
16.613. Okay, and then the unit vector in the direction of u, you're just dividing every component by this magnitude. And so you got -4 divided by 16.613, +14 divided by 16.613, and -8 divided by 16.613. And can someone tell me what those values are? -0. What? 241. Okay.
0.843. -0.482.
482. Okay. So that is in the same direction as this original vector u that we got. And since it's in the same direction as this vector that's perpendicular to our 2 input vectors, this unit vector is also perpendicular to our 2 input vectors. Quick, someone do this in your head. What's the magnitude of this unit vector?
1.
Very good. So that's the definition of a unit vector. It's a vector that has a direction, but the magnitude is 1, the length is 1. Okay, and they're very useful in dynamics and a lot of physics applications. All right, so that's 1. So let's say, let me try to draw a picture here. So let's say that these are our 2 original vectors, okay? And we came up with a vector that's perpendicular to both of these. Okay. So we got one unit vector that's perpendicular to these. Just looking at that picture, what's the other direction that's perpendicular to those two green input vectors? Yeah, it's the exact opposite, right? And so to get the exact opposite vector, you just take the negatives, multiply each component by -1 or multiply that vector by -1. So the other unit vector perpendicular to those two input vectors is positive 0.241, negative 0.843, positive 0.482. Okay, here's another random question unconnected to this problem. What if I took the cross product of these two unit vectors? What would I get? 0. The cross product of any two parallel vectors is 0. I also could have, okay, so think about this. We got this first vector u by crossing 1, 2, 3, and 5, 2, 1. What if instead I had crossed 5, 2, 1 and 1, 2, 3? I mean, that also should be perpendicular to each of those two vectors because it's a cross product. What would I have gotten as my output vector for that if I just switched the order of those two input vectors? Well, yeah, for the magnitude, it would have been the same. What I would have gotten for the cross product would have been positive 4, negative 14, positive 8. If you switch the order of two vectors and take the cross product, it just gives you the negative of your answer. Okay. Okay, so that was number 4. Let's go through a couple more of these. So number 5, what are the two unit vectors perpendicular to 5, 1 and -1, -1? Okay, so first of all, those two vectors are in the xy plane, right? So you can think of these, you can always think of two-dimensional vectors as these things with 0 for the z component. So let's think of it as 5, 1, 0, negative, and -1, -1, 0. And if you wanted two perpendicular vectors to these, you could take the cross product, and then you could calculate the absolute value and divide the components by the absolute value, and that would work out fine. But if you think physically about what's happening in this problem, you don't have to do that stuff in this case. Both of these two things are in the xy plane, right? So what's a unit vector that's perpendicular to the xy plane? 0, 0, 1, the z-axis, right? And what's the other? And so then what's the other unit vector perpendicular to the xy plane? Yeah, 0, 0, -1. So if you notice that, then you have more time for, eating ice cream and watching TV. If you don't notice that, you have to take the cross product, divide by the magnitude, and all that stuff. Okay, either way works fine. And what number did I go up to? 11 on the assignment, is that right?
Yep.
Okay. So all of this stuff up through number 9 is related to what we just did, so I'm not going to do any more of those. How would you come up with the components of this vector, or I guess what I'm asking for here is the coordinates of that point P. How would you come up with that?
5 cosine of 210 and 5 sine.
Perfect. Yep. So if you go, this works for coming up with coordinates of points, and it works for coming up with components of vectors. So if this is your coordinate system, and this is your vector, well, let me use the actual vector, I guess. The magnitude of this vector is 5. So you can always just write the components of that vector as the magnitude times the cosine and sine of the counterclockwise angle from the positive x-axis to the vector, which, like Alex said, it's 90 to get to the y-axis, 180 to get to the negative x-axis, then another 30 gives you 210. And so that gives you 4.33 negative and negative 2.5. That's the components of that vector that I drew, and it's also the coordinates of that point. You also could do it like if you're doing it in your head. You can also think of it just in terms of right triangles, come up with the lengths of the legs of the right triangles, and then think about what quadrant you're in for the signs. But this way always works. And that makes it nice if you're ever writing a computer program or something. Like I said, my goal is to come up with ways of doing things that require as little thinking as possible. And so this is really good that way. And then number 11. Okay, so what are the components of these two different vectors from A to B and B to A? So a vector that goes one point to another point, you can get that by coming up with the coordinates of those 2 points and subtracting the destination point minus the starting point. It doesn't matter where you put your origin, so you might as well put your origin at the starting point. So let me, let's see, 3.5 and 3.2. Okay, so this is the point A, and this is the point B. And we're given that this distance is 3.5, and this distance is 3.2. Okay, so first, what is the vector that goes from the point A to the point B? Okay, so I'm going to put the origin here. Just think about the origin there temporarily. And then all I'm doing is calculating the coordinates of that point B in this XY coordinate system. So with the origin at A, the coordinates of B are, well, how do you get there? You have to go 3.2 in the positive X direction. And then you have to go 3.5 in the negative Y direction. And so that's that. Exactly right. Yep. So for B, then it would just be negative 3.2, positive 3.5. And you could also do that by putting the origin this time down here at B, and then calculating the coordinates of A in that coordinate system, and that'll give you the vector going to A from B. Okay, so this stuff, none of it is like that hard, but you need to get comfortable with it. Because we're gonna be doing a ton of it, and the last thing you want to do is when the other parts of this class get hard to be sometimes getting hung up on this stuff, you know what I mean? So we'd like to get comfortable with this right away. Okay, so now let's go back to ordinary differential equations. So this is part of our mathematical preliminaries. And we're on number 4. This is solving ordinary differential equations using separation of variables. Okay, so you can use separation of variables for any problems of the form. Let's write it as D, what am I going to call that function? So let's call that D big F dq. I'm just trying to come up with just representative random variable names. And these are equal to a function g of f times a function h of q. Okay, so what does this mean? So for example, let's say that we have the function, the problem, y dot is equal to y squared t squared. Does this meet this form? Yeah, and maybe to see it, you might have to fiddle with it a little. But remember that y dot means dy dt.
Y dot equals dy dt.
Yep, that's the definition of the dot, is the time derivative the total time derivative. And then that's equal to y squared times t squared. And you can think of this function g of t, g of, let me do it in the order I said. So to satisfy the form we have here, we need g to be a function of our dependent variable. What's our dependent variable in this problem? Our dependent variable is y, and our independent variable is t. Okay. In these differential equations, the thing that you're taking the derivative of is always the dependent variable, and the thing that you're taking the derivative with respect to is the independent variable. Okay, so like in this case, the dependent variable is capital F, and the independent variable is Q. Okay, so to satisfy this form, what's the function of our dependent variable in this differential equation? Y squared, yep. And then what's our function of our independent variable, t? T squared, yep. And then we're just multiplying those two functions together. Because we have dy dt is equal to g of y times h of t. Okay, so as long as you have that format, how do you solve this? So to solve, move all the things involving the dependent variable to one side and all the things involving the independent variable to the other side. That's why it's called separation of variables. You're separating them to their two sides. So get all dependent variable stuff on left, let's say the left side, and all independent variable stuff on the right side. So with our function, our general function here, we're going to have df over g of f on the left side. And on the right side, we're going to have h of q dq. So for our example, how does that work? We're going to get, so this is our example, dy dt is equal to y squared t squared. So we're going to get all the y stuff on the left side. So we have dy over y squared on the left. And on the right side, we have t squared dt. And since we have a dy on one side and a dt on the other side, we can just integrate both sides now. So we're going to take the integral of dy over y squared, and that's equal to the integral of t squared dt. Okay, well, what do you get if you do these integrals? I can rewrite this as y to the negative 2 dy if we integrate, we get negative y to the negative 1. And that's equal to 2t plus, I'm mixing the two constants together, putting the two constants together. What?
You derived.
Oh, I did. Now I'm out of practice. Okay. T cubed over 3. That's better. Thank you. Okay, so this says negative 1 over y is equal to, I'm going to write this as t cubed plus 3c over 3. And now take the reciprocals of both sides, and you get y is equal to 3 over t cubed plus 3c. And there's a negative, so I'll put the negative here. Okay, so now we have what we want, and that is the dependent variable as a function of the independent variable. That's always our goal with this stuff. There's one thing that's a little bit unsatisfying about this. What's that? About this answer? Exactly. That constant can be anything. In order to get a complete solution, we need to know C. Okay, we need to know what that constant C is, and that comes from the boundary conditions that have to be given with these. And since every derivative that you have is going to have a constant of integration, you need one boundary condition for every level of derivative. If your differential equation has a third derivative, you need 3 boundary conditions. If it has a second derivative, you need 2. So you need one boundary condition. That's a terrible way to word this. I have this worded in my notes here. So notice. For an ordinary differential equation of order n, okay, so if n is 3, then the highest derivative is a third derivative. If n is 2, the highest derivative is a second derivative. What was n for this example? 1, yep. So for an ordinary differential equation of order 1, you need n boundary conditions. Okay, so let's do this problem again. I'm going to just use the same example I did before, but this time I'm going to give a boundary condition and show how to find that constant c. So, okay, let's say we have y dot is equal to y squared t squared where y for t equals 0 is equal to 10. Okay, well, we have dy dt is equal to y squared t squared. So y to the negative 2 dy is equal to t squared dt. And we can integrate both sides. And we get that negative y to the negative 1 is equal to t cubed over 3 plus c. That's what we had before. But now we're going to use that boundary condition to find that value of c. Okay? So we're going to plug in t equals, you can see that this boundary condition is at t equals 0. Okay, so plug in t equals 0 and y, what's y at this boundary condition? 10, yep. And then we can solve for c. So we have negative 10 to the negative 1 is equal to 0 cubed over 3 plus c. Everything's a number except c, so we can just solve for c now. So c is equal to negative 0.1. Update our solution. So this is our solution, although it's not in the best form yet. But now we know what c is. So we can write this as negative y to the negative 1 is equal to t cubed over 3 minus 0.1. And now you could go through the whole thing again. So let's say negative 1 over y is equal to t cubed minus 0.3 all over 3. Take the reciprocal of both sides, and y is equal to negative 3 over t cubed minus 0.3. And if you don't like decimals in your fractions, which is very reasonable, let's say negative 30 over 10t cubed minus 3. Yeah. None of the math on these problems is hard. What's hard is keeping track of what you're looking for, what's the dependent variable, what's the independent variable. Okay, like if you can do that, you're halfway done with the problem already. Okay, let me do an example that has a higher order derivative in it. Okay, so let's say that our function or our differential equation is x double dot is equal to 2t squared where x of 0 is equal to 2 and x of, actually let's do it with x dot at time equals 2 is equal to 4. Okay, well, I'm going to rewrite this in the DDT notation. So you can think of this as d squared x over dt squared is equal to 2t squared. And we're going to do this problem in 2 steps. Okay. But each step is just what we did in the last example. So I'm going to actually think of this as d dt of x dot. Okay. It's d dt of dx dt is equal to 2t squared. And we want to get all the x dot stuff on the left side and all the t stuff on the right side. Now, remember that in order to use separation of variables, you have to have a function of the dependent variable multiplied by a function of the independent variable. The function of the independent variable, t, is obvious there. That's the 2t squared, right? What's the function of the dependent variable in this case? It's just 1. Okay, it's a pretty boring function, but it's just whatever you have to multiply to this function, to this 2t squared function, to get the whole thing on the right side of that equation. So we have dx dot is equal to 2t squared dt And now we can integrate both sides. So this becomes x dot, and this becomes 2t cubed over 3, and then we have our first constant of integration.
C1, is that what you're saying that is?
Yeah, I'm calling that C1 because we know, since we have a second order derivative, we know we're going to have a second constant. Okay, so you have two choices for the boundary conditions. You can keep this C1 in and keep plugging ahead, or often you can solve at the halfway point for the constant that you have. In this case, we could solve for it right now. So to solve for this boundary condition, to use the boundary condition to solve for this constant, we're going to plug in t equals 0 and x equals, oh no, we're going to use the other one, sorry. We're going to plug in t equals 2 and x dot equals 4. And we're going to plug that into this equation that we just got. So we have 4 is equal to 2 times 2 to the third power over 3 plus C1. And now we can solve for C1. Let's see, 8/16 divided by 3 is 5.3 repeating, right?
Yep.
And that's negative plus 4. And so we get this constant that's equal to negative 1.3 repeating. And now we can update. This is what we knew x dot was before. Now we know a little more because we know C1. So x dot is equal to 2 t cubed over 3 minus 1.3 repeating. Are we done? Well, how do you know you're done with an ordinary differential equation? When you have the dependent variable expressed as a function of the independent variable. But x dot isn't our dependent variable, x is. Okay, so we need to do this again. You know, so the second step, we're going to start with dx dt is equal to 2t cubed over 3 minus 1.3 repeating. Our function of the independent variable is all this stuff that we see. Our function of the dependent variable is 1 again. So we have dx is equal to the quantity 2t cubed over 3 minus 1.3 repeating times dt. And now we can integrate both sides. So we get x is equal to 2t to the fourth over 12. I'm going to write that as t to the fourth over 6 minus 1.3 repeating times t plus a second constant of integration and how do we find that second constant of integration?
For the same condition, last one, t equals 2 x dot equals 4.
That's very close to right. That is the right idea.
What was the opposite?
Now we use the other boundary condition. The reason we need two boundary conditions for a second derivative is we need to use one for each integration, basically. So now we're going to use the boundary condition that says when t is equal to 0, x is equal to 2. So plug that into this expression here. We have 2 is equal to 0 to the 4th over 6 minus 1.3 repeating times 0 plus C2. So C2 is equal to 2. And now we just have to update our expression one more time. And we have x as given as a function of t is t to the 4th over 6 minus 1.3 repeating times t plus 2. And now we have our dependent variable expressed as a function of our independent variable, so we know we're done. Any questions about that? Okay. Now, there's really only one more way that this can get more complicated when you have higher order derivatives. What do you think would happen? Do you think it's possible to do this problem if, say, instead of that boundary condition saying x dot at 2 is equal to 4, what if that boundary condition said x at 1 was equal to 8? How do you think we would approach something like that? Because notice, then after our first step, we couldn't have used either boundary condition. Do you see that?
Well, maybe depending on when we get x double dot. I think it would be 8 power.
Well, we would do the same thing for the first step that we did before, but when we got to this first boundary condition after the first step, we wouldn't have anything that we could plug in because we don't know anything about x dot. Okay. So how would we approach that? Well, the answer is we would go all the way through, keep both constants of integration until we're done. We'd have this expression that would have C1 and C2 both in it. Then we do both boundary conditions and solve a system of two equations for two variables using what much beloved function on your calculator? Yeah, reduced row echelon form. Or you could solve it by hand, it's only 2. Depending on how many derivatives if you had. If you had 40 derivatives, then you'd probably want to use reduced row echelon form. Okay, let's do one like that. Okay, so let's say that we're given that the acceleration. So let's say this is a one-dimensional free fall problem. And we're going to use the fact that the acceleration is the time derivative of the velocity, and the velocity is the time derivative of the position. So if the acceleration is negative 9.81, what's the position as a function of time given that at time equals 0, the position is 10 meters or whatever, and at time 1, the position is 8.
Should we expect any conversions within these equations?
No, everything will be SI units. I won't make any of that complicated. Yeah, things are complicated enough. Okay, so how are we going to do this? Well, first there's a little bit of interpretation here. Notice that since acceleration is v dot and velocity is p dot, acceleration, that means, is p double dot. So our problem really is p double dot is equal to negative 9.81. And these are our two boundary conditions. P of 0 is 10, and P of 1 is 8. Okay, so I'm going to write this like I did last time as d dt of P dot is equal to negative 9.81. Separate variables. We'll think of that negative 9.81 as the function of time, and 1 is the function of P dot. So we have d P dot is equal to negative 9.81 dt. And we can integrate both sides. So we get P dot is equal to negative 9.81 t plus C1. This is where in the last problem we used the boundary condition to find C1. Can we do that here? We cannot, because neither of these boundary conditions says anything about P dot. Okay, and what we have here is an expression for P dot. Okay, so we're just going to have to keep that C1 in it and just keep going. So now we'll go to step 2. So we can't use a boundary condition yet. So step 2, we have dp dt is equal to negative 9.81 t plus C1. And so dp is equal to negative 9.81 t plus C1 dt. And we can integrate both sides. And we get that P is equal to negative 4.905 T squared plus C1T plus C2. Since we couldn't use either boundary condition at the halfway point, we have to use both boundary conditions now at the end. So our boundary conditions. The first one says when time is equal to 0, P is equal to 10. So plug these into the function that we have right above, and you get 10 is equal to negative 4.905 times 0 squared plus C1 times 0 plus C2 . And so C2 is equal to 10. And now we'll update our function. So P is equal to negative 4.905 T squared plus C1T plus 10. And now we'll do our second boundary condition that says when time is equal to 1, position is equal to 8. And I'm going to use the updated function that we just came up with. So 8 is equal to negative 4.905 times 1 squared plus C1 plus 10. And so C1 is equal to, what is it?
2.905.
Yeah. Negative 2.905, yes. Minus 2, thank you. And update. And you get your final expression for position as a function of time. Negative 4.905 T squared plus 2.905 T plus 10. And you can remember from physics 1, what we have here is an initial position of 10 and an initial velocity of 2.905.
Sorry, can you repeat that? Our initial position was 10.
Yeah, that's what we came out with here. This is our initial position. This is our initial velocity. You don't really have to remember that, but that's just connecting this to stuff that you've done in Physics 1. Okay, so we did not have to use reduced row echelon form or substitution or anything to find the boundary conditions here because of one of the choices I made about the boundary conditions. And that is, it was because my first boundary condition had time equal to 0 here. If I would have instead had two boundary conditions where time is not equal to 0, then look at this first boundary condition here. Because I had a time equals 0, it made this C1 term go away. And that let us just solve for C2 directly. And then we could solve for C1 directly. But in general, on these kind of problems, you know, if I hadn't given you a boundary condition where time is equal to 0, you would have had two equations for two variables that you would have to solve by substitution or RREF. Okay, any questions about that? If you ever see a partial derivative, you know, you don't have to worry about it because we're not doing that in this class. You can just draw a big X through it. And you'll deal with that in 4 years or whatever when you take that stuff. I don't know. Yeah. So hopefully there's a lot of those. That's what you're hoping for, because partial derivatives are these things if you haven't seen them, like the squiggly D's. Have you ever noticed that if there's ever like a movie about like a math genius or whatever, the way they show you that he's a math genius is he's doing partial derivative stuff on glass with a marker? Like that's just shorthand. Like, we don't want to waste a lot of time with this. Just trust us, he's a genius. He does partial derivative stuff on glass, you know? Oh, yeah. Yeah. So, I mean, you can go to college, go to your 4-year school and bring glass with you everywhere and write these, and everyone will think you're really smart. Okay, so that is separation of variables. Ordinary differential equations. So remember, ODEs mean one independent variable. In the last two examples, that was time. Most often, it's going to be time in this class. But you can have more than one dependent variable. In this class, we'll only do uncoupled systems of ordinary differential equations. What that means is that each dependent variable stays in its own equation. Okay, so for example, if you have a system of equations that says x dot is equal to 5xt and y dot is equal to 2y squared t squared. And you have your boundary conditions. We can solve this because there's an x equation and a y equation. Okay, and the way you would solve that is you just treat it like it's two separate problems. You do the x problem first, and then you do the y problem second. Okay.
So an example of standard one equation would be, this is not an example, but trying to calculate the position of a falling object based on the velocity.
Yes. Yep. That's a perfect example. So if you're in a projectile motion, you're trying to calculate where something's going to be as it goes through this arc. That would be an uncoupled system of differential equations, and you could solve for the x and y components, of the position, just one by one. Here's what we won't see. We won't see problems like x dot is equal to x, y, t, and y dot is equal to x squared, t squared. And the reason we won't see that is there's a y in the x equation and there's an x in the y equation. Really, we only need one of those to throw it out. We don't need both. But that's the definition of a coupled system of equations. There are ways to deal with it, but we're not doing it. So you don't have to, if you see this, you're done with the problem. Yep.
Any particular reason
why we won't do those?
Is it just out of our scope?
It takes more digging into differential equations, and this is where we're going to stop.
5 pages in on the assignment.
Yeah, I mean, it's not terribly complicated, but we're just not going to do it. And if you can get comfortable recognizing the stuff that we are going to do and get to the point that every time you see it, you can solve it, you'll be way, way, way ahead of the game going forward in your mechanics classes. So what we're doing with differential equations is plenty. We don't need any more. Okay. Okay, so that's it for math preliminaries. And so on Tuesday, we'll start getting into kinematics, which is just relating position, velocity, and acceleration vectors of particles. So next, we're going to do particle kinematics. Who remembers what kinematics is compared to kinetics? What's kinetics and what's kinematics? It's really annoying that those names are so similar. I feel for you on that one. They didn't invite me to the meeting where they named those. I was too young. It was 400 years ago or whatever, but kinematics is just describing motions without the causes involved. Kinetics includes the causes. So kinematics is position, velocity, and acceleration. Kinetics brings force into it. Okay, for now we're just doing kinematics. And remember, I'm going to keep bringing this up because it's a very important distinction. We're going to be starting with particle kinematics in non-rotating coordinate systems. Okay, that's all. See you Tuesday.
Do you know if the bookstore by chance has any rentals for TI 89s by chance?
I have one you can use actually, if you'd like to.
I would like to rent it.